Okay, excellent. Thank you. I thought I could steal a few extra minutes, but he's already timing me. Yes.
Could you remind me what the worst case aspect of it?
Excellent. So good. So let's remind ourselves how we got the A hat. A hat was the solution for minimize, let's say, minimize nuclear norm of a variable that you are interested in, such that, and this is a 3-order tensor that you want, and in our case it's n by n by n, such that xijk minus aijk, this over, aijk, y, because y is what we are observing, okay, which is a noisy version of ijk in omega, which are the observation, and m is the number of observations that we have. We want this to be less than or equal to delta. And delta was the bound a priori that we knew, where delta was 1 over m summation ijk in the observed entry, the L1 norm of the noise. And we knew that sort of this is delta. Now, in a sense, I can allow delta ijk to be arbitrary. You can choose subject to this constraint. And there's, of course, another constraint, but for the purpose of presentation here, I'm going to ignore it. But it will sort of, I will hide it in the proof because I'm going to skip some details. But this is necessary, some bound on infinity norm is necessary. You can't put everything into, let's say, if you have m things, one option is to put all your m amount into one element and 0 everywhere. That's not allowed. You need to be sort of bounded. You could allow it potentially to grow like maybe square root of m2, but not like m. All right, so let's say it's reasonable. I know this bound a priori, or let's say a bound on this, something like this, that I'm going to use here, and then I'm going to find you a solution such that that solution is in average across all entries, not just over observed entries. Across all entries is within a small error, where this error, if m is large enough, will vanish and it'll retain the same error on average. So that means that sort of we extrapolated in a sense now. So now this is the generalization aspect. So this is a good segue for me. So thank you for asking the question. This is it allows me to generalize my error on observed entries to all entries, including non-observed entries. And if, say, m is scaling like n, the total number of entries here are n cubed. So from n to n cube I went, so I generalized it really well. So if you, as a learning theorist looking at this, you will say, aha, this is exactly the generalization bound style argument that needs to be done. That means all I need to do is go back into all these recent development that has happened in last 10 to 15 years and connect it to somehow Rademacher complexity, bound the right right classes Rademacher complexity, and hopefully if I did everything right, then this would be my empirical error. This is my generalization error that I want to track, and this will be the Rademacher complexity related term. And if that happens, then I'm done. Okay, and that's exactly the proof plan. So the proof plan is that argue that somehow this term is captured through the Rademacher complexity of the model or the sort of the solution class that we are looking at, and then sort of just argue that this is that kind of statement. Okay. Again, coming back to the adversarial part, I'm allowing this, but now of course, if I had a nice Gaussian model, then this is weak, because this leaves me constant error, versus if it's a Gaussian model, then I would expect errors to vanish. And all of the convex optimization based proofs were this kind. They always have that. So it's kind of errors never vanish. And when they say things are recovered because you never have this. That is why delta ijk is 0, and you either observe or you don't observe. So you don't observe fully, you observe only partial entries. So there is a noise there in the observation, but not in the once observed entries are exactly observed. And in that case, you recover things exactly because delta is effectively 0. All right. So how do we prove this? First, we say that, let's say this is the true error or error over all entries. Let's call this kind of error, which is error restricted to, let's call it, this is empirical error in this case for x, but with y replaced by a. Okay, so I'm abusing notation here. We want to bound this by this plus another term. Okay, so with that, let's define the first part first. So let's define Rademacher complexity of this nuclear norm with m samples as expectation over omega sigma. So these are the random things which I'll define in a second. Supremum over x nuclear norm less than or equal to 1, or we can keep equals to 1 because it's going to be, so let's just keep it 1. 1 over m absolute value L equals to 1 to up to m sigma L x IL JL KL. Okay. So what is omega? Omega is, as before, a set of indices which are, so omega is drawn uniformly at random set of size m drawn from these indices. So it's without replacement, other way to think about it. Sigma is Rademacher variable, that is, it's uniform over plus minus 1, and this sigma is just a collection of m Rademacher independent, identically distributed Rademacher variables. Okay, there's plus minus 1 with probability half each. Okay, and now we are computing expectation of this quantity over these random selections. So I'm fixing an x. You fix an x, which is a 3-order tensor, okay, such that it has nuclear norm equals to 1, okay, which means that a bunch of things. If you remember, the way we had defined nuclear norm was set of all tensors which have that kind of a decomposition, but decomposition in terms of its components, that is, effectively it's singular vectors, okay, with abuse of notation. Singular vectors were incoherent vectors, okay? And all that means is that sort of the sum of the singular values was 1. That's why it's sort of probably, it was like a probability distribution. And so for all such x's, take any particular x, look at sort of the deviation that you can get by taking this out, take the absolute value, of course normalized, you're taking supremum over all such thing, and then you're taking expectations. So you're looking at the maximum deviation, in a sense. Okay. And so that's the quantity. We will argue later that, let's say lemma 1, we'll argue that Rm scales like square root of n over m. Okay. In particular, if I increase this to r, let's say then simply one way to think about this is every entry of this is r times larger. So it's linear in that. So if I have, let's call this 1, or let's call this r, then r would be like this. Okay. Yes. Supremum is inside, expectation is outside.
So if you fix the sigma, can I then choose an x?
Yeah, that's exactly right. That's exactly right.
So I can make the signs line up.
Exactly, and that's why sort of this is going to be sort of almost like a worst case bound. If it was the other way around, it would be sort of a lot more nice and contained. Great point. In a sense, this is kind of trying to prove worst case bound, and that's why it will be help us sort of prove the generalization error. So this is lemma 1. So let's assume that if I did not get to this, this is one of those this is the type of calculation that you would do like this. What you will do is that one way to calculate this, right? Suppose I give you one fix, remove this. I give you one fix x, and you wanted to evaluate this. You'll say, okay, I don't know what that is, but ignore this absolute sign for a second. I've got this random variable, which is +1 -1 over m values. If this is each of these entries bounded, then really what I'm looking at is I've got sum of m random variable. I'm looking at its deviation, which has 0 mean. So I expect it to scale like square root of m, right? Okay. So this would scale like square root of m. I've got 1 over square root of m here. That gets me this. So where is my square root of n coming? My square root of n is coming because of the supremum. Why is that coming in? Because of the following reason. Let's look at this set. Okay. Now, one way to look at supremum of many things, if I, let's say I've got L random variables, each of them have deviation square root of m, and let's say they've got exponential tail, I'll expect that maximum to increase like maybe log L or square root of log L, depending on your sub-Gaussian or sub-exponential. But let's say you'll have log L times square root of m. Okay? Here, this is let's say think of a ball of dimension n, then you're really trying to pack it nicely. And that means that if you're trying to pack it nicely within epsilon balls, then it will have 1 over epsilon to power n such different things. So that means that you're looking at log of exponential in n, which is n times this, okay? And sort of now it's because it's sub-Gaussian, it's square root of log L, that is square root of n. And that's where you get square root of n by m. Okay, so let me repeat again how the proof goes, roughly speaking. If you remove this, and if you let's think of this as 1, just hypothetically. Okay? So then you're looking at sum of m IID random variables with 0 mean. So we all believe that square root of m is the right thing. Okay. Now, if I have L such random variables, and because they are sub-Gaussian, the maximum of them would scale like square root of m times square root of log L. Okay. Now, the question is that how many does this lead to? So there's one clever argument, but subject to that clever argument, effectively it boils down to saying that let me take the set of all such x's, there's a whole space, let me sort of discretize it, basically, pack it into epsilon balls. Let's say half-size balls is also enough. The number of such balls would be scaling exponentially in n, 2 to the power n. So now my L is replaced by 2 to the power n. So my maximum would be square root of this, which is square root of m times n, and that divided by m gives me this. Okay, so this is simply a union bound, nothing more than that. And sorry. No, I'm simply sort of x's are not independent for every different x. So every different x can lead to different deviation. I know that. And now I'm trying to bound worst case deviation. And the way I'm doing is worst case deviation by just packing the space of all possible x's and doing this silly union bound using this sub-Gaussian tails. Yeah, exactly.
Yeah, this maximum of Gaussian argument works when the Gaussians are independent.
Well, these are independents, not these ones. Exactly. So this is sort of like in some sense, I have a set where the set is these guys, and this is just sort of different directions in which I'm looking at how far am I going. Okay? And that's how sort of I will get square root of mn. So the only part is that sort of why is this what it is? Okay, let's say that's exercise. Now, interestingly enough, this is also the way you would do, let's say yesterday I sort of showed you how we would do, or maybe we didn't do that. You could do, if you wanted to bound the spectrum of random matrix, this is exactly the type of thing you would do, because one way to think about random matrix spectrum is, let's say M is a matrix, so I'm doing X transpose M transpose MX, and I'm trying to bound this, then I'm doing sup over X equals to 1, right? So first I'll look at this, and I say, well, this is nothing but if the rows of these are Mi, so Mi transpose X, X transpose summation over I, these are independent rows, let's say. Now this is a one variable, this is another variable. If this is Gaussian, then this is a Gaussian too. So I'm looking at a Gaussian square, that is a chi-square, some of those, independent of them. Again, sort of I will get sort of exponential tails, and then I will do packing of this, put everything together, you will get exactly that square root of n perturbation. Okay. So it's exactly the same argument, that's why I wanted to do that too. So I'll erase this, and now, let's say this lemma is done. So now the question is that how does this lemma help us finish this proof? So this is the standard theorem from past. I don't know who is the right person to attribute. There are, I think the first one was, I think Bartlett and somebody who actually sort of used some of these things. But before that, of course, Vapnik and Chevronic have these arguments into their thing for classification. So maybe in interest of time, I will just state the basic result, and then we'll leave it at that. So what the basic result says that error in X is less than or equal to empirical error in X plus, let's say, constant times Rademacher complexity of the nuclear norm plus some constant times okay. So this is my error. This is the delta is the bound on empirical error. So I think there's a 2 here. I missed it. Delta is the bound on empirical error. Let's say 2 delta. This one is R times some constant times square root of n over m. I forgot some logs somewhere. There should be a log somewhere. Okay, and then this term will go to 0. So really, it's only this term that matters. This is always fixed. So as long as m is larger than this, my empirical error is going to be less than or equal to 2 delta. Okay, I will leave, I will not prove this, but this is, this follows by basically the symmetrization argument that Vapnik and Chevronic used in first time in their thing, and then later generalized for regression setting, and this is regression-like setting. Okay, any questions? Okay, so here's a nice implication. So what is implication? If similar argument will go through if there are matrices, that means that for matrices, if you have M that scales like number of samples that scales like R square, N log square N, then if delta is 0, then you recover exactly. If delta is not 0, you recover within error delta with these many samples, because same analysis goes through. The same thing holds even for 3-order tensor. That is, the sample complexity is not changing with the increased order, which is remarkable, right? The difference is that this optimization problem, for matrices, we can solve it as a semi-definite program. For tensors, we can't. And actually, it's a hard problem to solve. There are, I think, computational reductions that exist there. So really, while this is the, let's say, n times r or n times function of r is the information efficient sample complexity, because anyways, you have n times r parameters already there. For matrices, you can achieve it. For tensors, you can't achieve it. In particular, I think the main result of Barak and Moitra was that they can reduce this problem to certain distinguishability problem, which under the statistical computational hypothesis would say that finding this kind of result would require number of samples that grow like n raised to 3/2, not linear in n for 3-order tensor. And they had a sum of square, some I think degree 6 proof, which requires n raised to something like 16 or something sample complexity or computational complexity. Okay, and that was that. Okay, now I'll switch to the. All right, so far we have seen these two parts. We just finished this. Again, I'll post all the PDF slides one way or the other, so that the other alternative proof, if you're interested, there is at least summarized in the second set of slides. For this proof, this is taken from Barak Moitra paper. I'm not sure if I'll be able to copy my notes. That is, they're not fully clean. Okay, now I want to sort of speak about, maybe for 30 minutes, very quickly about non-convexity part. I was sort of commented on tensors, so maybe I'll sort of quickly go over it, and then one black box application. So let's say 15 minutes each. I'll skip roughly this. All right, so non-convex part. Okay, so far we saw the matrix factorization, the non-parametric method, convex relaxation, and now the iterative non-convex methods. Okay. So just to remind ourselves again, right? A is ground truth, Y is the observation for part of entries, and expectation of Y is equal to A. We want to produce A hat so that error is small. Okay. All right, and one of the non-convex algorithms was this, right? That is, I want to find U's and V's such that they are as close as possible to my observations over a set of entries that I've observed. And I want to minimize this optimization. I want to solve this optimization, and this is not convex. Okay, and and now the reason there is a hope that this will work is, let's suppose that Y is not noisy, but Yij equals to Aij, and omega is not a subset, but all the entries. Then what is this problem? Well, this problem says that I'm trying to find the rank R approximation, best rank R approximation of my matrix, and we know that for a variety of reasons, wherever you learned it, we know that that is a unique solution, and this can be solved through, let's say, power iteration for that matter, right? Iterative algorithm. Okay. So that means that at least in the exact setting, we know how it will work. So the question is, why shouldn't it work in not exact setting? In particular, if I ran this iterative algorithm and it found a minima, let's say a local minima, would that be a spurious one? Of course, in the exact case, we know that it won't be spurious one. So would it be spurious one where I'd added a little bit of noise or I'm missing some observation, right? Putting it other way, how robust is this view in terms of having the local minimas being global minima effectively for this kind of a problem. All right, so the whole point of this paper and subsequently this paper is that local minimas are global minima, and they are sort of provide excellent answers in some sense. All right, so let's sort of look at some kind of a near optima initialization. And in a sense, this is where all of the intuition for this started. All right, so here is revisiting the proof for SVT, but for rank R matrix. Okay, so remember that we had argued that suppose Y is the noisy matrix, this is its mean, and the deviation has a spectral norm that scales like square root of MP. Okay, this is what we saw yesterday. If you carried out argument like this, you will convince yourself of that as well. Okay, so we know this. Now let's say that A has rank R, which means A looks like this. If it's incoherent, or as we had discussed, the incoherent vectors in this case, that would look something like this. That is, the norms are bounded above like this quantities. Okay? And because every entry of A is nothing but UI transpose Vj, and that's the absolute value of that, the bounded above by this multiplication, that will lead to this kind of a bound. Okay? That means when you have incoherent singular vectors, every entry of your matrix is bounded above by your rank divided by square root of Mn. So it's actually a very nice matrix. Okay? So really all the theory is about nice matrices. I mean, if your sort of matrix is sort of in terrible shape, there's no hope to recover it. Okay. Using this and this fact, we get that sort of, well, this quantity that is now divided by P, A minus 1 over Py, that sort of in this, the spectral norm of this matrix is no more than R divided by square root of NP. All right, so what does this bias? Well, this is what it biases. This says that sort of the truncation of Y is an excellent approximation for a Frobenius norm. Okay, now, yesterday we didn't do this calculation because we had a matrix which may not have been low rank. But in this case, we are explicitly assuming low rank. And that's why it's easier to do calculations. So let's do that. So let's say P squared times this quantity turns out to be, because A hat is the truncation of Y, times P minus A, which is less than or equal to 2R times this. Why is that the case? Well, these are the sum of the singular values, square R of them. They must be less than or equal to R times the maximum one, and that's what I'm doing. Now, this quantity, I can rewrite is through, let's say, this kind of inequality as this. Effectively, triangular is inequality, but on squares. Okay, now, this one, if we look at this one is less than or equal to this one. Why? Well, YR is the best rank R approximation of Y with respect to either Frobenius or spectral norm, which is one of the really nice fact. It means that if I take another rank R matrix, it will only be larger than this one. So that means this quantity is an upper bound on this, which means I get this. That's great, right? Because now I know how to bound this, like this. And so put everything together and you get A hat is like this. What this means is that if P is larger than R cube over N, you get your result, which is roughly this type of result. Now, okay, you got one extra R, and I've lost a little bit, I've been a little bit loose, but the point is this communicates intuition again. That is, if you don't sort of worry about getting exact R, this simple calculations will get you roughly what you want. So what that means is that if you started by taking your observations, doing rank R approximation, you already get an excellent initialization. That is, you're in a good neighborhood. And now, from there, you run your local algorithm or your iterative algorithm will converge into effectively your global minima. The reason is that these guys characterized this local neighborhood of incoherent ground truth. In particular, ignore the details. All this says is that let me find all of the matrices which are around A in the Frobenius norm sense, and they are incoherent and all the nice ones. Then within this neighborhood, the Frobenius norm minimization with regularization, where regularization is coming from nuclear norm, is locally convex. Okay, that means that sort of you got sort of the you got shape like this, at least locally. And you are locally into this neighborhood because you did truncation. So you are already in the local neighborhood, and within local neighborhood, these guys did careful calculations to argue that it's in that neighborhood, this function is convex. So that means that sort of you do your gradient descent and you will find your minima. Yep. Yes, so take your observation, replace missing values by zeros, do rank R approximation, A hat equals to just this.
And then you will be in the local neighborhood.
Local neighborhood of things because of this kind of thing. And once you're in local neighborhood of that, this analytic argument of Sun and Luo would say that, hey, actually, it's a pretty good local neighborhood. You're effectively convex. Now you have exactly what you want, and now you sort of keep minimizing iteratively U's and V's, and you find what you want.
The only thing it's telling you it will converge.
Sorry?
The only thing it's telling you it will converge.
Well, you will converge because this is a monotonic algorithm. Yeah. All right. So that was the sort of the Sun and Luo argument. These three authors, Gay, Lima, went a little step further, and they said, actually, you know what? All the local minimas are global minimas, so we don't really need this kind of initialization. And that calculation is nice and simple. So I thought I'll take you through it. It's 5 minutes. Okay. So we'll do that for rank 1 setting and no noise. Okay. So let's do that. So how do we define local minima? We define local minima of a function f as a zero gradient point, and where your second order is let's say it's positive definite, right? So you got a curvature like this at least locally. If you are trying to get rank 1 minimization, let's say I have observation y, and I want to find the best rank 1 approximation. One way to write that is as follows. That is, only restrict yourself to indices which you have observed. That's this definition, that's this notation. And up to them, what you do is you take y minus rank 1 approximation, and you're doing this writing in trace form, so that's just Frobenius norm, or Frobenius norm square. Okay. We want to understand how do local minima of this function g look like, defined as this. In particular, ideally, I would like to say is that the local minima of this G is the best rank 1 approximation of matrix Y, because that's what I'm looking for. Okay. So let's forget that it's Y, let's forget it's partially observed. Let's assume that we have a true ground truth matrix A, which I'm looking for. Okay. And of course, in this case, we do know that this has to be best rank 1 approximation, right? Because of our old classical understanding. So let's do that classical understanding in this function form, in this definition. That is, let's sort of rederive the fact that we already know for 30, 40, 50, 60 years, whatever that is. So let's write down the gradient and the second order. A little bit of calculation will suggest that it looks like this quantity for gradient and this quantity for second order, okay? Just a trace calculus. All right, so now we can sort of set this to 0, and then sort of say there is some x that sort of satisfies this. That's a local minima, and then we want to ask question, how does that look? Now, before we go further, let's say A is symmetric matrix. What will be the solution of this? It's the largest eigenvector, okay? So let's sort of argue that the local minima of this is the largest eigenvector, okay, and then we are done. So first of all, local minima of 0, local minima means this, which means this is 0, which means that this is equal to this, which means that this, which already says that at least x is an eigenvector. So that's a good step forward. Now we want to argue that it is the eigenvector with the largest eigenvalue. So let's suppose not. And suppose that there's an x star, which is the eigenvector with the largest eigenvalue, okay? And it is not local minima, but x is local minima, which is another eigenvector. Because this is local minima and because this is PSD, this must be true. If this is true, I can expand this using this definition, and I get something like this, okay, whatever I get. Let's sort of collect few things. First of all, these guys are orthogonal to each other, so it has to be 0. I collect these two things. Well, x star is largest eigenvector, so that means lambda times this is that, what I get here. And I know that sort of this is what this quantity is, so x star remains here and x star goes out, let's say. So I've forgotten the normalization part. But whatever that is, no, actually this is norm 1, yeah. So I'm left with this one, and since this is greater than this, I get this negative. But that's a contradiction, right? So that means my assumption is wrong. That means that the local minimizer must be the largest eigenvector. Okay, good. So at least we got what we wanted in the good case. Now let's understand the robustness of this. In particular, how much do these things get perturbed when we have a random setting? In particular, let's say partial observations. And okay, so in that setting, you do the same calculation and keep this p omega, which is this effectively this projection type operator. Then you get this kind of calculus worked out. Again, let's look at local minima, which would satisfy these kind of equations. Okay, and then a little bit of calculation would suggest that if x is a local minima and let's say z is a global minima, you will get answers like this. This was one condition, and this is another condition. Putting these two conditions together, effectively you will conclude that z transpose x must be equals to x square must be equals to z square. Okay, and which means that z must be x. And the reason we are able to do that is because the type of inequalities we obtain without this random perturbation are exactly the tight ones, which are sufficient. With the perturbation, we have got small perturbations sitting here. And because these are inequality proofs, not equality proofs, perturbations are okay. Okay? And the reason perturbations are small because we are looking at the linear functionals, which involves lots of variables rather than one or few variables. So that's why concentration happens. Okay, so 2 points. Like, whenever you want to look for robustness, always look for inequalities rather than equalities. That makes it easy. And second is that whenever you're looking for random perturbations, always look for aggregation, because aggregation sort of removes the noise. Don't look for things that involve few variables. So those were the two insights that sort of concluded this proof. Okay. All right. So with that, let me move to the last part. All right. So this is just before we go forward. This is the scorecard so far, right? So the singular value thresholding, if you look for, okay, so it's 2 by 2, low rank structure or Lipschitz functions, and arbitrary noise or no noise or Gaussian noise, okay, or additive noise. And then there's norms like MSCs or max norm, or if no noise, then you're looking for exact. And roughly speaking, if you look at the matrices with rank R, n times R is what you want, what you have, And n times r is what is needed because that's roughly the lower bound. If you go for Lipschitz functions, arbitrary noise, n raised to, let's say, 2 minus 1 over r is what you can get, where r is the dimension. As dimension increases, effectively you need everything. If you're looking for additive things, then you can sort of actually remove the dimension dependence, but with additive noise. And if you were looking for max norms, maybe with arbitrary, you can get roughly n log n. Okay. And for non-convex setting, the best sample complexity we know is nr log n, and that was for low rank additive setting for MSc error, or low rank no noise and exact, this paper by Keshav and Montanari and O. For example, this analysis is a lot weaker than that analysis because, first of all, it doesn't do much of additive noise. It is robust to noise, but it is sort of n times large power of r times many logs. Okay? And in this business, people do care about getting the exact r and getting exact logs, right? So that's that. Okay, so now let's say no lower bound, but lower bound is super easy to argue that if you wanted MSc going to 0, and if your rank R setting, you must need P scaling like much faster than R over N. Okay, there is a nice computational lower bound conjecture which says that if you have arbitrary noise, let's say at least 0, 1 noise, because of community detection is a special case of this, you need n times R square samples. But we don't know sort of whether this is tight or there's even further tighter lower bound. Okay, so there are all sorts of questions, even the conjectures are not clear. For tensors, if we do the same nearest neighbor cell algorithm that we discussed before, you can get max norm, you can effectively get the threshold, and you can get n to the power 6 complexity, but it assumes the latent variable model. If you assume incoherence, then there is this paper which gets you approximate error. It got few polylogs here, and it has got n to the power 5 sample complexity. Okay, there's a nice neural network view of this world. You can do non-uniform sampling also, where you can sort of think of the probability with which you are sampling things is also another a matrix estimation. The first what you do is that you just look at the mask, which entries are observed or not. That's a 0-1 problem, and you use that to get Pijs. Then you actually look at the observations. The observations are actually P in expectation Pij times Aij. So you calculate that, and then you divide it by Pij. Now, in this case, you really want sort of fine control over P's. If P's are sort of extremely small, then this approach will not work because you're dividing. What do you do if you can't divide? That's a great question. Because if you can do that really well, then you would be able to just solve things like stochastic block model directly from this. Okay, now I'll sort of talk about one of the black box application which actually you can solve for, say, time series imputation or forecasting using this as a black box. So let me sort of skip these things, and I'll come back to these function models, but let's suppose, okay, so let's suppose here's a question. So I've got some function of time. Think of finite sum of harmonics, think of polynomials or some of those things. Okay. And now what's happening is I'm observing random variable x of t. So let's say instead of t being continuous at t integer times, so at every integer times I'm either observing or not observing, and when I observe it, xt is a random variable which is Poisson with parameter f of t, and let's assume this is non-negative. Okay. So I'm observing zeros and zeros, ones, so integers, not all the time, only some of the time, and from these observations I want to recover this. It's like I've got a hidden state which is continuous, and I'm observing a noisy version of which is discrete. The question clear? And the question is, how do I recover this? Okay. So from x's, produce x hat, so that x hat and f, the squared error between them over all the integer t's is small. Okay. So, yeah.
How do we get samples to the why is that a valid approach?
Well, I'm just saying, let's suppose hypothetically it is what it is. And you don't know that the noise is Poisson, okay? You're just observing integers. It could be that it could be sort of some other multinomial distribution that you have over integers as per which you are generating. For you, observations remain the same. You don't know what your noise model is. You don't know what the latent function is. But from these observations, you want to recover that. Okay. So here is the algorithm that will sort of use matrix estimation as a black box. So what you do is that you will take your time series the way you have. I'll create a matrix. I'll apply matrix estimation, and I'll do undo transformation, and that's it. Okay, so what's the transformation? Okay, it's a pretty complicated one. Okay, so here is my time series. Let's say if I've not observed, then some of them will be question marks or stars, and that's fine. Just look at them, keep it then. And then you choose some parameter L, keep them in blocks, and then just stack them up like column like this, and that's it. Okay, so your time series, you stack them up like this in columns. It gives you matrix. You do your favorite matrix estimation method. Okay, that will give you x hats. Let's say x hat 1 would be exactly the proxy for f1. Sorry. Okay, so this one after matrix estimation will be proxy for f1, f2, and so on. Okay, and the claim is that this would work really well if you had a matrix estimation method which had good, let's say, MSC estimator. For example, if you used singular value thresholding, and let's say your t samples, you had roughly square root of t by square root of t matrix created, then let's say if you had what I call linear recurrent formulas, like LTIs, then the number of samples required to get within error epsilon would scale something like 1 over epsilon square. And then there are other models. Let's say if it's polynomials or let's say logarithm in t, that would require something like this. Okay. And good, so one of these, okay, so let's sort of understand what they are, let's say. So this is called page matrix. Apparently in controls literature, people had, other than Hankel, in 1981, somebody in controls community had sort of proposed this as a way to look at rather than Hankel. I learned it from the control school in ETH. Well, it has a name. It's actually called Chinese page matrix. Chinese page matrix is the transpose of this, so I'm calling it page. I don't want to call it Indian page matrix. That would be silly. But in any case, so this is the page matrix, and it looks something like this. One way to think about page matrix is it's a subsampling of the columns of the Hankel matrix, right? Because all I'm doing is I'm sort of skipping L things in the Hankel, and then I'm going and jumping like that. Now, let's suppose you have a time series or say function f that's underlying satisfies following structure. That is, f of t plus s is f of t times f of s. If you have that, and if you look at Hankel, then actually Hankel would look, it's actually rank 1. The reason is that sort of ith row and jth column of Hankel would have some such form, and hence it would look like this, which means that every ith row can be decomposed as has the same one fixed parameter, and j varies like this, which means this is a rank 1 decomposition. That means a function like this has a rank 1 Hankel. If you have Hankel rank 1, then page would be rank 1, because this is just subsampling of the columns of Hankel. Okay. Now, if you take these kind of now functions as your sort of atoms, and look at linear combinations of them, of course you will get rank R version because things just are additive. Okay. Now the question is how general or how restrictive it is. Well, going back to our high school algebra, right? You look at cosine. Cosines have nice such forms, right? I'm sure we learned somewhere in trigonometry. So now this already says that, hey, I've got, this is like this with two things. So that means that sort of every harmonic component actually gives me 2 rank. So I've got sum of k harmonics, then it's like I'm getting 2k. Okay. If I've got polynomials, again the same thing applies. You can do xt, xt square, all that. So that means whether it's a polynomial also, you got sort of finite rank. You got harmonics, you got finite rank. If you actually got exponentials also, it works out fine. Or you can sort of put all of these guys together. There's some term which is exponential with harmonic, with polynomial. Again, all of them will nicely decompose. Like this, okay? And then you can say, well, actually, you know what? I might have something like a Lipschitz function which is transforming this LRF. In that case, it won't be exact, but then you'll be approximately low rank. Or you have, let's say, things like logs of harmonics or square root like this. Or you have sublinear like logs and all that. Again, it will be approximate. So these are the classes of functions for which is reasonably representative. Okay. I mean, at the end of the day, we know that any realization of a stationary sequence, right, is not really finite, but it's a kind of a stochastic integral over harmonics. So if you believe that that stochastic integral is actually a nice Lebesgue integral, not stochastic, then it's a finite sum of harmonic. Okay. All right. Here are just some plots saying that this is kind of a state-of-art algorithms, and this is where it is, and RMS is small. So it's sort of nice. These grays are observation of a Poisson process. Red is the predicted mean, and the blue is the true mean. And it's good that you're not seeing reds, right?
How many oscillations?
Oh, in this one, I don't, 0.9. And this is some other such plots. All right, well, it is ended. Oh, that's okay. So just one last thing I wanted to say is that, well, this is like imputation. What if you want to do forecasting? Turns out, at least in all of these models, after you do low rank approximation, because of nice time series structure, it turns out you can just do linear regression. And that's one way to sort of actually do the one way to do the time series forecasting. That is, you take the same time series matrix. First, you denoise it by doing matrix estimation. Then you look at the last row as your target and remaining things as of your features and do linear regression, do that model. For future thing, what you do is that take observations, project it onto the column space of this, and then do linear regression, and that will be the way to do your forecasting. And again, if you had a matrix estimation method which is not good at MSC, but actually it has to be good in terms of MRSC or max norm, then you will be able to prove something nice for all of these class of models. And when you use that kind of a method, you would sort of find that, let's say, this algorithm will beat something that's a best R library and things like that. Okay, so if you look at this as a regression problem, and if you sort of remember your regression literature, this is called what's called principal component regression. That is, you got feature matrix, you got labels, you take your feature matrix, apply PCA on it, which is like one instance of matrix estimation, and then do linear regression. The reason you would do PCA, at least classically, was to reduce collinearity, so to speak. But now, even if you have missing values, you have arbitrary noise, that's okay. That means that if you wanted to analyze PCR, surprisingly, it's been around since 1980s, but there's no analysis of that. you want to analyze it, you want to sort of actually have a good matrix estimation analysis with respect to this norm, or maybe max norm, not the MSC norm. And then if you do that, then you get sort of nice results. Okay, so hopefully I've convinced you sort of in last 3 lectures that this is an interesting topic. If you're not sort of part of the party, it's not too late. There are lots of interesting questions. It's just getting started. All right, so with that, thank you very much for your attention.